Okay, hello, guys. Hope you're doing well. Um, I'm going to discuss coordination compounds and complex ions because I thought the pre-lab video was really bad and complex ions are fun and one of my favorites, and I feel like it didn't do it justice. So I thought I would supplement with my own video, and I might post it to YouTube. We'll see. But I'll be discussing everything about complex ions, doing a lot of examples. And just talking about them briefly. So, just to review, from the Lewis definition of an acid and a base, an acid is a molecular ionic species that can accept electrons. And these would be forming an coordinate covalent bond that's also known as a complex species. A base is an ionic or molecular species that donates a pair of electrons when you're forming a coordinate covalent bond. And a Lewis base is also known as a ligand. You'll see this word a lot. So your Lewis base is always your ligand. It is donating the electron. Many metals, especially the transition metals, are Lewis acids, and they form complexes with your typical Lewis bases. So your Lewis acid is always going to be the metal, and your Lewis base is always going to be the ligand. Now, there is something known as monodente and bidente ligands. Now, all this means is that when you are drawing the attachment of a ligand, if you're drawing the structure of a molecule, a monodente ligand is going to just connect once. It's going to have a single bond. A bidente ligand is going to have a double bond. Now, this polydente ligand, known as ethylene diamine tetraacetic acid, EDTA, is polydente. That means it can form a lot of different ligands. So you don't really need to know that one on lecture. We might have to do it in the lab, but it's not bad. But the common monodente ligands are the fluorine ion, chlorine, bromine, iodine, sulfur, mononitrogen dioxide, cyanide. So all of these common monodente ligands. The most common ones that you're going to see are these two right here. The water and ammonia, both are neutral and don't have a charge. Now, the only two bidente ligands you need to know is the oxalate ion, and that has a -2 charge. We typically will write it as OX when writing the formula of the complex. You don't have to, but it just is an abbreviation. And the other one is ethylene diamine, and we represent that as En in the formula, and this is a neutral atom. It has no charge. So monodente, one attachment, bidente, two attachments, polydente, many different attachments. And ligands are the name given to a Lewis base. So these are some steps for writing the formulas for the complex. I'm not going to read them because I'm just going to do it. An important word here is a chelate, and it's the Lewis acid-base complex when your ligand is bidente. This is known as a ring structure, and I'll show you some examples of that in a minute. So just to show you two examples of a complex ion, here we have a complex ion formed with copper 2. We have 4 attachments here of ammonia. We have 6 attachments here of ammonia. However, I wrote, or whoever made this, decided to write these two as H3N, just the reversed way. Because you can form many isometric formations of complexes. So it doesn't matter, but they decided to write the NH3 a little different here, but you have a copper ion with 6 ammonia attachments as ligands. The Lewis acid here is the copper, and the Lewis base, the ligand, is the NH3. Now the coordination number refers to how many attachments are on the molecule. Here we have 6 attachments on the metal, so the coordination number is 6. When you write the formula of the complex, you put a bracket, you put the metal, you put the ligands, how many, and you put the formal charge of the entire species. Here the formal charge is +2 because the copper is +2 and the NH3 is neutral. So you just end up with +2. The other one I have here is ethylene diamine tetraacetic acid. That's the EDTA. This is a polydentate ligand because you see you have many attachments here. There's also many areas for chelation because you form ring structure. These two are areas for chelation. These two are areas. These two are areas. These two are areas, and you can also have a chelation here because you have a ring structure. I think that might be a question on the lab, but this is another common ion example. Now, there's also common biological complexes, things that you would find in biology. I believe this is also a lab question. This structure here is vitamin B12. Now, as with all complexes, you have to have a transition or a central metal here. And if you search, you could find the metal right here. That's cobalt, so that's the metal in vitamin B12. Here, this is hemoglobin. If you've taken biology before, you know hemoglobin's important in the regulation of red blood cells and the filtration of iron. So hemoglobin has a central metal of iron right there. Okay, so I believe I have a couple examples on how to handle these complex ions. So we'll just get started here. So a complex ion is formed from a copper 2 ion and 4 hydroxide ion groups, and it wants all of the following. So the first thing I'm going to do is simply write the formula for the complex. So I put a bracket, I put my copper, because it's copper 2, I put my hydroxide. Now I have 4 of these hydroxide groups, so I'm going to put a 4 there, and the bracket, and I need to put the charge. Well, the copper has a +2 charge, and the 4 hydroxide groups have a -4 charge, each with a -1 charge. So you get the formal charge on the complex to be -2. So that goes right up there. What's the coordination number of the metal? Well, this is going to be how many attachments it has, how many ligands. If you look at the structure of this complex, you have copper as your central metal, and you have 4 Lewis bases, the hydroxide groups. So the coordination number corresponds to how many ligands you have. Here we have 4 attachments. So the coordination number is 4. Put a little line here. Identify the Lewis acid. Well, that is going to always be the metal. The base is always going to be your ligand. And your ligand is always going to be your Lewis base. Could the complex be isolated as the chlorine or potassium salt? So all the instructors ask this question. It's a weird question. I'm not sure why they ask it, but I'm going to go over a couple examples. All this is saying is if you were going to form a salt with this complex, would it be a positive salt, the potassium, or would it be a negative salt, the chlorine? And here it would be a positive salt. It would be the potassium because you have a -2 charge and you want it to become neutral, so you're going to need a positive ion, which is the potassium. Now, if I'm going to write the formula for the salt, I'm going to put the metal on the outside. And now notice potassium has a +1 charge. The complex has a -2 charge. So I'm going to need 2 potassium. In brackets, I just rewrite the complex. And that is it. Do note that there's no charge on this complex now because we neutralized it with the salt. Okay, given the following complex, identify the following. The coordination number of the metal, the Lewis acids, bases, and ligands, and could the complex be isolated as a chlorine or sodium salt? So let me draw this complex here. I always like to draw them. Not that you need to, but I think it's kind of fun. This is silver ion in the center, has a +1 charge, and I'll show you how you can tell in a minute that it has a +1 charge. So your structure would look something like this. You know, you could have an isometric shape here, so the NH3s could go anywhere. I knew that the silver has a +1 charge here because the NH3s are neutral and the complex has a total charge of +1. So the only thing that could be contributing to that +1 charge would have to be the metal or the Lewis acid. So I know it's a +1. So the coordination number refers to how many ligands or attachments you have on the metal. Here, that's going to be 2. The Lewis acid, like I just said, is the silver ion. The Lewis base is NH3. It's a common weak base, and as always, the Lewis base is the ligand. And here we have another question. Could the complex be isolated as the chlorine or sodium salt? Well, the complex has a positive net charge. So if we want to neutralize this, we would need a negative ion. So in this case, we would choose chlorine as the salt. And if you wanted to write the formula for the salt that's formed with the complex, you would just put a chlorine out front. You don't have to put a subscript for the chlorine because we only need 1 because the total charge on the complex is +1. So that 1 chlorine neutralizes it to 0. So we would choose chlorine here. All right, another complex ion is formed from chromium 3, 2 ethylene diamine groups, and an oxalate group. And we want to write the formula for the complex, identify the coordination number, draw the structure, and could the complex be isolated as an iodine or lithium salt? So this one's a little bit more interesting. Chromium +3 charge. I have 1 oxalate group, so I'm going to write that as OX. Now each of these has a -1 charge, but if you recall, oxalate is a bidentate ligand, so it's going to form 2 attachments. The ethylene diamine is also bidentate. It will form 2 attachments, but it's neutral. It doesn't have a charge, so I don't need to worry about that when writing the structure. So that handles part C. So the coordination number here would be the number of attachments that chromium has, the number of ligands. Now here, be careful. It's not 3, it's 2, 4, 6. Because oxalate and ethylene diamine are bidentate ligands. The formula for the complex, well, we have chromium, we have the ethylene diamine group, we have 2 of those, and we have the oxalate ion. What's the charge of the complex? Well, chromium's +3, ethylene diamine is neutral, and the oxalate is -2. So the formal charge here, or the charge of the total complex, is a +1. Now, could the complex be isolated as iodine or lithium salt? Well, once again, we have a positive charge here, so we're going to need to neutralize it with a negative charge. And iodine has a -1 charge, so we could isolate it as an iodide salt. So if I was going to write the formula for the salt, I would put iodine as on the outside, only need 1 of them because it balances out the +1. I would have my chromium, my ethylene diamine groups, 2 of them here, and my 1 oxalate ion. And once again, don't write the charge because it's no longer an ion. So this is probably one of the harder examples because you got to remember that these are bidentate ligands, the oxalate and the ethylene diamine. If you don't remember that, you're going to draw the structure wrong, you're going to draw the formula wrong, you're going to write the formula wrong rather, and you're not going to get the coordination number right. So you have to remember that oxalate and ethylene diamine are bidentate ligands. One final example, Write the formula for the complex ion formed between the metal ion chromium plus 3 and 6 nitrate ions. So we have chromium again, we have nitrate, and we have how many? 6 of these. Wow, that doesn't look too good. Formal charge here, well, you have a positive 3 and a negative 6 here, so your total charge is minus 3. The structure of this, well, I would have chromium in the center, and I'm going to have 6 ligands or attachments. So it doesn't really matter how you draw that, because remember, if you learned in Chem 1, I keep saying there's these things called isomers, which is just another way to draw a molecule, similar to chelation. And that's 6. So coordination number of the metal chromium here would be 6. See, put that as coordination number. Because it has 6 ligands. Now, could this complex be a chloride salt or a potassium salt? Well, here we have a negative formal charge, so it would be a potassium salt, because potassium is positive. So if I was going to write the formula for the salt, well, I would need 3 potassium, because I need to balance out that minus 3. Then I would just rewrite the complex. But remember, I'm not going to include the charge here because it's no longer an ion because we neutralized it with the salt. Well, I hope this helped you to understand complex ions. I had fun, one of my favorite topics. If you have any questions, please write to me about the lab. But I think I covered what you'll need to know for the lab. Pay attention to your oxalate and your bidentase. These are some biological complexes. We discussed chelation and ethylene diamine tetraacetic acid. So this should help you with the lab. Hope this helps. Let me know if you have any questions.